Hello, everyone, and welcome to the Audio Product Development Alliance. I'm Roger Shively of Shively Acoustics International, and this is the APDA, or Gateway to Audio Product Development. This is the only organization that focuses exclusively on audio product development education, providing current relevant content that can be experienced in person, live online, or on demand. And combined with valuable cross-industry knowledge sharing, the APDA serves as a networking hub for the audio industry, offering access to experts and colleagues for professional development. The APDA is where we can come to learn how to build relationships and to build better audio products. Online with us today from the APDA, as well as myself, is Steve Willenberg from LinkPlay. Hello, Steve.
Hi, Roger. How you doing? We're looking
Doing
forward
good.
to a great session and welcoming Jinlan. Very exciting.
Yeah, and also from the APDA is Dave Lindbergh from DB Enterprises and the THD podcast. How you doing, Dave?
Hey Roger, nice to be here. Another automotive session from
Yeah.
Roger is great to listen in and find out what's happening.
Oh, well, you always have the best questions, though, Dave. So it's okay. And then our media, I'll mention our media partner, which is the Audio Express, and our member from there is Joel Martin. So we're very grateful for their support as always, and very grateful for the support from behind the scenes for those of us who are putting this on. And we are recording today, so you can see this on our YouTube channel, and it will be kept there in the archives as well, so you can watch it at any time. Those of you watching online in that stream, you can jump into the chat and ask us questions so we can pass those on. And subscribe if you haven't already. Please join us there. And you can also follow us on LinkedIn. And so, in speaking of which, we have some upcoming events that we'd like to briefly talk about. One of them is coming up next week in Barcelona, and the APDA will be there at the event at the ISE, which is the Integrated Systems of Europe. And we're going to be co-sponsoring a meetup with the OCA, the Open Control Architecture Alliance, at their booth on Wednesday, as it says there, February 5th. Their booth is in Hall 7. It's E260, and it'll be at 2 p.m. on Wednesday of next week. But you can look around. You might find Joel Martins hanging out there, but you'll definitely see Dave.
Mhm.
So look for him and say hello, and maybe ask a little bit more about what the OCA is as well as the APDA. OCA is concerned about the AES 70 open control standard, so let's see how that works for you and how it might be relevant. But also just follow us on the APDA, keep current on what we're doing. So once we have that going, we have also coming up next month in February, near the end of it, we'll be putting on another webinar, which should have a topic of concerning tariff strategies and the product development process. So look forward to that. We should be bringing that into the stream by the end of February after we get done with the ISC, and then we have events throughout the year. So keep track, and we'll be keeping you informed. So without anything else, I think I'm going to say hello to Jinlan. How you doing? She's from COMSOL, Principal Applications Engineer at COMSOL, and welcome today. We always say happy when Jinlan shows up because it's always a good deep dive and good information on what COMSOL can do for us. And today we're going to talk about automotive acoustics and how it can be how it will be using COMSOL's multiphysics. So welcome, Jinlan.
Okay, thank you, Roger, and hello, everyone.
Yeah, so I think what we'll be talking about, like I said, the applications, the latest developments in simulation technology for acoustic analysis in the automotive environment, and discuss how we can model and analyze performance of sound systems and vehicle design itself, thanks to these new tools in multiphysics. And I know, Jinlan, I won't go too far ahead of that, but you're going to be talking, I know, about some new time domain analysis for acoustics from COMSOL, but also how the GPU engine can be used to help improve the simulation times and efficiencies. So with no further ado, let's jump into into what you have to show us from COMSOL. We're looking forward to it. Go right
All
ahead.
right, thank you very much. So let me share my screen first.
Yeah.
All right, let me open my presentation.
There you go.
Very
Looking
good.
looking good.
Okay, thanks again, everyone. So welcome. I'm really glad to have this opportunity to share with you how COMSOL can be used to model and analyze automotive acoustics. I have to say this is a very big topic since the relevant applications span a very wide range, but all for one purpose, that is to study and optimize sound behavior in vehicles. Let's start with a very quick overview of the key applications. First of all, noise and vibrations. These are typically the sound that we don't want to hear. They may include powertrain noise, which is originated from like engine, gearbox, or exhaust systems. And then aerodynamic noise, such as like the wind noise from roof racks or a side mirror, or it can also include air duct noise, like from your air conditioning systems. And squeak and rattle noise caused by friction between parts that are not properly secured or need lubrication. I actually have this problem with my car now. This morning, I can feel the vibration and hear the fluctuating noise when my car is at the parking mode. So I know something is wrong. and then like the tire noise generated by tire road interactions. So these are the noise that we want to minimize. Simulation can help to predict and address the potential issues early in development.
So what you're talking about there is determining what the noise path is, the transfer path, whether it's acoustical, but also there's mechanical aspects of that as well.
Yeah, mechanical aspects and especially the sound pressure level, like if you can predict how loud the noise can be, right, based on like the possible conditions you will confront. So though all those you can like, if you can predict beforehand, and then you can mitigate by using solutions. So then the next is car cabin acoustics. It regards the design of the sound that we do want to hear. This can include, for example, optimizing speaker placement for stereo or immersive audio. These are the hot topics, right, nowadays.
Yeah.
And also creating personal sound zones or using microphones and speakers to boost the clarity of conversation. Now you need to model microphone and speakers, their interactions. And also designing voice-controlled smart systems. We also know this is a very, very hot topic, and this is the trend. And many vehicles now feature AI-powered voice assistants. And finally, those ensuring like sensing applications that use ultrasound that we cannot hear, like ultrasonic parking sensors, and also like tire pressure sensors, which use surface acoustic waves. Of course, there are also applications that are not listed here. For example, the design of acoustic alerting systems in those silent electric vehicles to create artificial sound for pedestrian safety. So there are all different kind of applications, and most of the applications involve multiphysics. Many require acoustic structure interaction for vibroacoustics, such as the study of structured bone noise or vibration-induced noise. Like in some cases, you also need to include electromagnetics, for example, when you want to study noise from an electric motor. So porous materials are widely used in the industry for noise control. We all know that. For example, particularly in mufflers and particulate filters. Electroacoustics is required for loudspeaker design, and also car cabin acoustics if we want to include the real speaker sources. And piezoelectricity are responsible for the operation of ultrasonic sensors.
And I think also when you talk about porous materials, but there's also poroacoustics where we're talking about these very small spaces in acoustic solutions, which come into play when we're dealing with meshes that go over loudspeakers, or we're putting a microphone in a position where it may have some boundary. That's also part of what you're talking about as
Yeah.
well.
Yeah. So like a poroacoustics, that's like a very efficient way to model acoustic in porous materials. So
Okay,
yeah. And I want to say like COMSOL provides solutions for all these multiphysics phenomenon and offers a range of numerical methods that can be used alone or combined to meet your specific needs. Let's take a closer look at the multiphysics and multi-method approach.
Quickly, before you get into that, you
yeah.
have those four possible. Are they all a single module, or are they separate modules that you put into your base modules that you have for maybe multiphysics? So each one of those are in part of the multiphysics module that comes with COMSOL?
Yeah, so these methods are seamlessly implemented into acoustic module. So you do not need actual product in order to use a specific method. So
okay.
They are all included in the acoustic module.
Oh, good. All right, good to know.
Very good.
Thanks.
Yeah. So I want to show you all these wonderful multiphysics and multi-methods approach in COMSOL with a simple vibroacoustic setup. So as seen from the screenshot, you have a vibroacoustic problem that requires physics interfaces for modeling structural vibrations here by solid mechanics and shell interfaces. And also you need physics interfaces for modeling acoustic in fluids, here pressure acoustics based on finite element method and boundary element method. So, so Roger, to answer your question, the methods are implemented into a physics like an interface. So you don't even realize, oh, it's a different method. It's basically you are using a different interface.
Okay, good.
Yeah, and COMSOL includes like built-in features to couple them all, which is defined under the multiphysics nodes. Now that's open. Open
I think that's
COMSOL
the power of the multiphysics approach.
Yeah,
there's simply an interaction, not a new process that you have to start over. That's good.
Yeah, very good. Let's open COMSOL and look at the physics interfaces and their couplings, so you have a better view how it looks like.
There we go.
Yes. So here we basically have a panel with air cavity inside and a speaker mounted to the panel. So you can imagine this is a very simple, simplified car door model, right? Then the door, like they are comprised with aluminum solid domains. These domains are modeled with solid mechanics. So they are simply modeled as a linear elastic material in this example.
Yeah.
And then the speaker is modeled by using shell elements. So these basically are very simplified surface elements in a 3D model to model very, very thin structures. Here you are able to specify the thickness of the thin structure, so you can have different thickness in different components. Here we simply just use one thickness. And in the shell model, here we simply apply a prescribed velocity in the y direction. This is the axis, acoustic axis direction to excite the speaker.
Yeah, so you can scale a large model into something that's a little bit more manageable. You don't have
exactly, especially for things very, very thin panels. If there's a lot, then you can save usually like a save computational resource, and then just model using surface elements, so you do not have to mesh the thickness.
You got it.
Yeah. And then we have acoustics. We use pressure acoustic frequency domain. This is an pressure acoustic implemented using finite element method. So this is applied to the air domain inside the cavity. And then we have boundary element pressure acoustics that is applied to the exterior domain, which is identified as infinite void here. So that means anything that is not drawn in the geometry. The exterior domain, this is modeled using a boundary element method. Now, all these are coupled, all the four physics are coupled under multiphysics. We have the acoustic structure coupling that couples pressure acoustic inside the cavity with solid mechanics. And then we have the acoustic inside the cavity coupled with the shell vibration. And then the acoustic outside, which is modeled by boundary element method, coupled with solid mechanics, and also acoustic outside coupled with shell. So acoustic are coupled to all the vibrations, and then the acoustic inside coupled to acoustic outside at this port opening boundary. So acoustic are continued.
Right.
And then lastly, the solid and shell physics are coupled at the edge, which they are all overlapping. So this guarantees displacement field are coupled, are continued. Yeah, so everything are coupled under this. So it is a very structured, organized way. If you right click, you can see this coupling are built in. You can just add in based on the need, based on like how you want the coupling to be done.
Yeah.
So just you could just dig further with this and like start adding the adhesives, like how you're assembling this, what goes in between those different shell and pressure acoustics components. You just keep adding to it and building what you're planning to build in real life.
Yeah.
Yeah. So like your geometry can be much more complicated. Yeah. So you can, as Dave mentioned, you can have like adhesive layer. You can have, like all very complicated. It can go like as complicated as it can be. Then and you might have porous material in this structure as well. Then you can add like a porous elastic waves interface if you want to like have a very detailed, precise model for the porous material. Then like you can couple everything together. It's all done underneath here.
Yeah,
and these are all building. Yeah.
Yeah, I think that's exactly where you end up going, Dave, for sure. We start kind of simple, so we make sure that the physics, the general physics, sort of makes sense, in a grand sense. And then as we see how that's doing, maybe we start to focus on, in particular areas, you may not need adhesive or anything everywhere, but just where you might find it important. And then that makes you a more refined model, but it's something that you can kind of work yourself to, like step one, let's do something very conceptual, and then step two, let's do something more refined so we can get the more detailed information that we need to make it more of a real product, basically, in the sense it's not just an analytical design. It's
it gives you those design freedoms, so that you can look at whatever aspect of it that's important to you.
You got it. And the beautiful part of this is the coupling that goes on here. And I think we'll get into that later on when we get to the time domain. But yeah, that's even better. So go right ahead. Thanks, Jinlan.
Sure. Thank you. So now we run, so of course you create a mesh first, and then And then we run the study. Here I just run like several frequencies. Then you are going to get these like a very nice default plots showing the displacement for different frequencies. All right, you are able to see like higher and higher modes start showing up when frequency increase. Then you are able to see the pressure inside the cavity, sound pressure level, then pressure outside. So this is like done by evaluating the BAM solution and sound pressure level as well. And COMSOL also create like default plots for showing the radiation pattern. So here is a 2D polar plots showing the radiation pattern for different frequencies. And also you are able to also get like a 3D, very nice 3D balloon data, like plots. So you will be able to see that. So yeah, I always want to start with simple to give you an idea. Then we're going to dive into more complex models. So let me go back to my presentation. Yeah, the example I show is relatively simple, right? But the principles is described are crucial in vibroacoustic applications. So let's dive into more examples in this regard. So this is a model for electric motor. It predicts the noise generated by an electric motor during its operation. This motor uses permanent magnets in the rotor and coils in the stator. The coils carrying a variable frequency current to generate torque, which result in vibrations not only at the frequency of excitation, but also at higher frequencies or harmonics. So the complete study includes a few steps. First, a transient analysis is to determine the electromagnetic force in the time domain. Then a fast Fourier transform is conducted to determine the contributions of like each of the harmonics. And finally, the vibration of the motor casing and its acoustic radiation is computed in the frequency domain. Now you see the left animation shows the displacement and acoustic pressure at a specific frequency. And in the right image, you can see the sound pressure level at half meter away from the motor. It's not difficult to notice that the radiation pattern has many lobes, right?
Yeah.
So meaning that the acoustic response depends greatly on the location of the listening point.
Yes.
Yeah. Here is a more complex model studying the radiation of sound from a gearbox. So now the vibrations are originated from the gears due to varying gear mesh stiffness. And they are transferred to the housing, resulting in acoustic radiation. The analysis also includes multiple steps. First, you run a vibration analysis to study the vibration of the gearbox. It uses a multi-body dynamics analysis. This is done, a transient analysis. Then the normal acceleration of the housing is converted again to the frequency domain and used as the noise source for acoustic analysis. Note this model, as well as the previous electric motor example, is based on a one-way coupling. Which means like you neglect the feedback from acoustic to the structure.
All right, thank you.
Yeah, this assumption is reasonable if the surrounding fluid is a light fluid, like air.
Air, yeah. Okay.
Yeah, you neglect the acoustic load on the structural vibration.
But when we go underwater, it's different,
Yeah, however, like for heavy fluids, you are right, Roger, you are ahead of me. So the unidirectional approach now is not valid for water, or oil. This is confirmed in this fuel tank vibration tutorial. Here, the tank is partially filled with fluid and is subjected to a vertical acceleration. So this study compares two methods for representing the fluid. One uses a traditional approach of like adding the fluid mass to the tank's wetted surface. So the fluid is not simulated specifically. The other is a full multiphysics approach where acoustic pressure in the fluid is modeled and fully coupled to the structural vibrations. The results from the two methods show significant differences, as seen in the plot on the right. Here, the data represent the transfer function from the applied excitation to the Z component of the stress at the mounting strap. You can see that the difference highlights the importance of accurate vibroacoustic modeling for predicting stress or fatigue in fluid-filled cavities. The left animation shows the warm-emission stress with deformation with acoustic pressure for the multiphysics analysis. All right.
Yeah. So that was both in acoustics, but I think you're going to eventually talk about how we may be doing that in the time domain. You mentioned time domain in the graphic.
Yeah, I mentioned, but yeah, I will show a transient model later. But
Yes.
yeah,
okay. Right.
but I just want to give you an idea what we can do in COMSOL.
Sounds good.
Yeah, we also have many examples of mufflers and particulate filters. So here shows some of them.
These are all online at the COMSOL webpage that you have some example.
Yeah,
okay.
so if you are doing like particulate filters, or you want to study mufflers, how to minimize the noise, you are welcome to go to our website and take a look. I want to especially bring your attention to this particulate filter example on the top right. So here is a new example showing that you are able to use a LAMP method to reduce computational complexity. So in this particular filter system, the filter itself contains over a few thousand channels. This is basically the filter is like what is amplified here. You have porous layers structure with long air cavities. So this here it contains, the filter contains thousands of cavities. So if you want to include all these cavities in the complete model, it's going to be very expensive. Now, to reduce the computational cost, the tutorial first performs a port sweep through the filter alone. It's only model filter. Then we can run like a port sweep to calculate the filter's transfer matrix. Then the transfer matrix can then be applied to couple to the surrounding like cavities to compute the total transmission loss.
Oh,
so
you can just ignore the fact that the filter is there, but just figure out the port and then the transfer function with the filter.
Yeah. Then then you can have like the same filter can be applied in different settings, right? So it can be represented by just using transfer matrix and apply at the boundaries. So it's like this provide a very convenient and efficient way to model the filter's performance in the larger system.
There was a question, maybe this is a good time to ask it. I don't think we need to go into too detail, but you talked about when you were setting up the model, there was the mesh, and that came in from a geometry that you either imported as a CAD or you drew. And if you're importing a mesh, is there a way to remesh it, or is there a process for, unrefining an area that doesn't need to be refined? Is that part of what COMSOL is available to?
Actually COMSOL has the tool now. With the new version, we have a very like a the tool is like improve the performance for remeshing. Yeah, you
Okay.
can bring in
Good.
a mesh, then you can create a geometry out of, or you can just remesh on top of the imported
Okay.
mesh.
Yeah, that was something that was in the chat, so I thought I'd get to it before we left.
Very good,
Good.
thank you.
Go ahead.
Yep. So yeah, we also have like ultrasonic car parking sensor. So this is very nice. You want to use a real sensor transducer here made of like a piezoelectric materials. So here you can, solve the transducer first, use a fan model to get the radiation pattern, and then that radiation pattern is used in ray acoustic to model, a given parking scenario. It's very nice example of combine different methods in one study.
Good.
All right, so yeah. So now I want to look into car cabin acoustics. This is a hot topic. A lot of people are interested.
Oh, yeah.
Yeah. So I want to say like COMSOL supports all different types of analysis, and you can combine different methods to obtain broadband acoustic behavior in response to real speaker sources. So there are several examples using the same cabin geometry. The sound is either emitted from a tweeter in the dashboard or a mid woofer in the front door. In these examples, the speakers are represented by TS-more parameters and coupled to the acoustic domain using the lambda speaker boundary condition.
Yeah.
So,
but to Dave's earlier question, if you want to get more refined, you can put a model result of a full speaker in the door module, perhaps, and then take the output of that and couple that to your larger cabin model instead of just using a teal small, which treats it like a plane but also you can take in the structural and the three-dimensional vibrational behavior of the loudspeaker too, if you want to get more refined. So yeah.
Exactly. Yeah, exactly. So so we have a lot of example. I'm not going to go to detail. I think many of you are already aware of this frequency domain analysis model for low frequencies, because you need to use a full wave-based method for lower frequency in order to capture the modal behavior, right? So this model actually solve up to 4 kilohertz thanks to an auto-generated iterative solver option. I'm going to show you quickly in COMSOL. I want to bring your attention to a new model for frequency domain analysis. This actually solves up to 10 kilohertz by using cubic discretization. This is a new model that we combine maybe a better combination of mesh element order with a solver. We have this like a higher discretization order allows for the use of a coarser mesh and an optimized iterative solver approach. So I have some number here, like for 10 kilohertz, the problem has around like 72 million degrees of freedoms, and it only requires like 235 gigabytes RAM, which is very doable, manageable in nowadays. And this model shows how to set up the solver.
So that the essence here is that you've got a higher order, like the cubic element. It has more higher. The element itself has higher discretization, so that your entire model doesn't require. It can be a little bit more coarser, and that improves the efficiency. Okay.
Exactly. So before, like usually typical, we use a second order, but this time, cubic order seems to be more efficient than for like this is for large models.
So
All right.
and you have that example model online as well?
Online as well. Yes, we
Okay,
do.
good. Yeah.
We do. Yeah. And then I'm going to skip that because I'm going to show you in the GUI. And then we have this hybrid, this model, which is ray acoustic model. Now you kind of solve a fan model of the speaker.
Right.
Yeah, this is a tweeter located in the dashboard. And then you solve a smaller fan model to get a realistic source because it includes the near field effects, right? From the refractions from the nearby geometry. Then the solution is used to as a ray source for ray acoustics. This is for like higher frequencies when a four-wave based method. It's not practical anymore.
Well, maybe ask the question, then when do you make that decision to go to ray acoustics? If you're saying the cubic model has maybe up to 10 kilohertz, the ray acoustics is going to take you into the higher frequency range beyond 10K to 16, 18 kilohertz?
Yeah. So although like I just show like you can run like a fan full wave up to 10 kilohertz, but you might not need to do that, go that high. You can, usually that is determined by like a shorter frequency, right? You estimate it based on the absorption of your surface and the volume. So that is something you can, but usually you want to go higher than shorter frequency. This is not a problem at all. Like in COMSOL, you can really go go up to the frequency that your computer cannot manage anymore. Then you can switch to ray acoustics.
Okay, got it. Thank you.
Yeah. All right. So yeah. So now you are able to combine the low frequency full wave solution with ray tracing solution to get the broadband.
You can get this post-processed inside of
Yeah,
COMSOL?
yeah. I'm going to. So now this is like you base it up like you get frequency domain analysis for full wave, you get the solution for lower frequency, and then ray acoustic for higher frequency. Then you apply this high, low and high filters to combine the solution. Yep.
And you're doing that by, it says concatenating, putting together the impulse responses.
Exactly.
So you're doing that as with, okay. Yeah.
We can do this inside COMSOL, and then this is explained in a blog and a example for room acoustics. But we also create a version for car cabin acoustics. Now I want to show that.
Please, yeah.
So Roger, let me know if I still have time.
Oh yeah, please. Yeah, I think we're good. Yeah.
So this is the so here you see like I have several components. So you can include like as many components as you want in the same model, and each component can solve for a different geometry for a different study, used for a different study. Now that's I have everything here. So this is like a four car using FEMs for lower frequencies.
Okay.
So what I have is frequency acoustics, like pressure acoustic in frequency domain. This is like a fan-based model. Now here I have this lambda speaker boundary. This is a tweeter here. So this is applied to the diaphragm, right? So, and then this is coupled to the electric circuit. This represents the tweeter. It's modeled by T-small parameters.
Okay.
So this is a standard SPICE netlist. So and the speaker, so the acoustic, so the speaker, the circuit is coupled to the pressure acoustic domain using this lambda speaker boundary. All right. So this like the current is which is the velocity is coupled back to the acoustic domain, and then the acoustic load on the speaker is coupled back to the circuit. So the load will be represented as a voltage.
Okay.
So these two are fully coupled. They are two-way coupled. So they will interact with each other, right? And then you can have like all different boundary condition here, absorbing boundaries. You can prescribe absorption coefficient or impedance, or you can define a porous layer. We have different options, built-in options you can use.
Yeah.
And keep in mind, this absorption coefficient can be also frequency dependent, right? So you can bring in measured data to take into account the frequency dependency, and
Got it.
and yeah, and also the seeds. So we have all these absorbance material included, and then we can, we of course we mesh the entire car. Then we solve the model using a frequency domain analysis. Here, this study, you can have many study, and this study only solves for the 4-wave components. You can see that. Yeah. And then you are able to get results for low frequency. All right. You can get different kind. Here we solve up to 1,000 hertz. You can get, and then you see like there's a sphere here. This is represent the location of microphone. Then we are able to get the microphone response. So here we plotted real part of the pressure detected by microphone and the imaginary part. So this is like the solution from the fan model, the 4-way model up to 1,000 hertz. Then we have the components we solve for higher frequency. Now for the higher frequency, we first solve for a fan model. Okay, here again, the similar the tweeter is simulated by using the electric circuit, and then we have a lambda speaker boundary here to represent where the speaker is, and then this is solved. Full model is solved in the study 1. Okay, here we solve for for component 2, and this we can get the solution for just this smaller domain. And I want to show you, and this shows the boundary, which is shows the surface intensity, magnitude, and direction. And this will be used directly. It's a very nice feature. You can use this directly in ray acoustics. So you can see like we have the pressure release from pressure field. We'll use the solution directly from this pressure acoustics and release rays from this surface for ray
You're
tracing.
basically feeding the full car cabin with this information from a submodel. So this is
exactly. So you just you do not have to like manually type in equations, but just call this solution from this physics, and then very similarly you prescribed in the ray acoustic model, you prescribe these absorption.
Got it.
This is exactly like the setup is exactly like the fan model. Right. And then you are able to run, let's go to
the full car?
No, here study 2. So here we solve ray tracing, see only ray acoustic here now. And then we run a parametric sweep to solve for all the frequency. Here NS just indicate a solution index. from the dashboard corner this study. So we are able to solve the ray tracing model, and then you will be able to see, you know, the ray trajectory for each frequency.
Got it. And then you can combine this results like you showed in the
Exactly.
previous. Okay.
Yeah, now we have the impulse response.
Mm-hmm.
You know, we can do FFT. So you are able to, from the receivers, again, we have a receiver. I forget to mention in here. So we have a receiver,
Mm-hmm.
the same thing there. So
Right.
this then the signal receiver received by,
Right.
yeah, the receiver then will be exported again, like the real part and in the imaginary part.
So we have
And
two
then
data
this,
sets basically.
yeah, we have two data sets. Now those data sets, now the component 4, we combine them.
Got it.
So here we basically have like, oh, the real part from Ray, the imaginary part from Ray, and also real part from, you know, the fan model and real part from the imaginary part from that. And then we have like a high pass filter and a low pass filter. And then this is combined using global equation. I'm not going to go through this.
Yeah, it's fine.
This is a template. Then you will be able to see after we run the model, we're able to, you know, combine, and we are able to get here.
Okay. No, that's
Yeah.
wonderful. This is new with 6.3, I'm guessing. Is that right? Or has it been there before?
This model is new. Yeah, this model is new. We have a version for room acoustics, but now we have a version for combined.
Okay.
And then, yeah, so, and you can do, finally, you can do IFT. So using this dedicated frequency to time, FFT, this will give you a broadband impulse response.
Excellent. This is great. So we are coming close. So before we finish, maybe you can talk a little bit more about the time domain solution and how GPU can benefit as well. So.
Yes, that's actually the next. Yeah, so this is a transient analysis, the same car geometry, and it computes the transient response to a Gaussian modulated harmonic signal. So the model is solved with the pressure acoustic time explicit physics interface. It have very nice features that allow you to incorporate frequency dependent damping on boundaries. So this is a real damping models can be used in the transient analysis, and the model is solved using an accelerated solver formulation that can be run on GPU. As Roger has mentioned many times, I know he's excited about this feature. So GPU support is new in 6.3.
Yes, it is.
So to give you an idea of the speed up, like here shows the performance. The model solved for 49 million degrees of freedom. That is like 30 acoustic cycles for 1,000 hertz signal. Yeah. Now on a modern GPU, this is done in 1.5 hours, compared to 19 hours when the same model is solved without GPU. Yeah. So this is about like a 13 times speed up. Yeah. We see an even like a bigger speed up for another case when GPU is tested for our wave-based room acoustic model.
That's great. And
yes,
I see that it was exclusive to NVIDIA cards. So is that still the case? And then eventually it'll be ported over to, well, at the moment we have NVIDIA. So.
Yeah, we are exploring like a more, actually more, let me show you the setup. Actually, I don't have a like a, because the model with solution is very big. So I have a like a, the model without solution, but I just want to show you, okay. You know, this is a pressure acoustic time explicit
Mhm.
And then here you have this is new. So here we can check this use accelerated solver formulation. All right. So you can choose compute, use GPU. Yeah.
Oh,
Even without GPU, if you uncheck that, you will get like a speed up, because we have like CPUs accelerated
okay. So that's
yeah,
with it's under the time explicit, the
yeah,
pressure
under
acoustics.
this
Got it.
specific
Yeah,
physics interface.
got
Yeah,
it.
and very nicely, like we actually support all these let me see. Yeah, this frequency dependent impedance condition. So here is done by partial fraction fit function. So you can basically what you bring in a frequency dependent admittance data,
Yeah.
and then you can fit into partial fractions using this dedicated partial fraction fit function.
Yeah.
So
Because that's basically saying that your absorption's not linear. It's not going to be, the car cabin's not going to be a
no,
linear space. And so that's what you first realize when you do the first model, and then you have to
exactly.
go out and find out where the nonlinearities are in your assumptions. And so, yeah.
Exactly. So you can bring in measure data, or you can get the frequency dependent absorption from from a submodel. Then you can fit into this, and then apply to the transient model. So
Okay.
I will actually have a webinar, a COMSOL done by COMSOL
Okay.
in next month. I'm going to talk about details about
Great.
using frequency dependent data in time
Okay.
domain analysis. Yeah,
Well,
if you are interested, you can come
okay.
and
Yeah.
learn more.
Well,
Yeah.
good. It sounds like there's going to be a lot of things coming up. And I think we'll probably have you back as well, so we can get into more details. We have a couple of questions that maybe we could quickly go to. There was something about a question about what should the settings of the impulse response be for the FFT. I'm not sure if I know that the full purpose of the question, but does it make sense to ask the question of what should the settings of the impulse response FFT be? I'm not sure. If you're taking the impulse response and then doing an FFT, is there anything that's specific to the settings?
Um. Let me see if I still have that model. So
Yeah, and I think everything you showed us today, you say is online or not online.
yeah, it's online. So you mean the
Okay.
settings, study settings for doing IFFT?
Yeah, if any of the models that you've shared with us today, you can go and
Yeah,
find
yeah.
them.
So
And
basically you this is a solution,
okay,
a study. Okay, specifically you can say I want to do IFT on a
yeah.
solution.
So you just have to
So
tell it the time. I mean,
yeah,
the
you just
frequency.
need to tell like, oh, what solution you want to get,
Yeah,
and then you get a like a range of time, and then you specify. Oh, we also have like different uh, window functions you can apply,
yeah.
and then you specify the frequency range.
Hmm.
Then COMSOL will do the IFFT for you.
Sounds good. Um, yeah, I'm probably going to have you wrap up now. So, and I think is there's any other questions, Steve or Dave, that we may have missed? I think,
I would just comment that anybody who's watching this in Legacy, just put your questions down below, and
yeah.
one of us will get to it and try to get some good answers for you.
Yeah, I mean, when it's online in the channel, we can take questions there even, and
Yeah.
we can keep answering these questions for as long as if somebody has a question. So that's not a
As long
problem.
as
I think
YouTube exists.
that's a that's a great thought, Dave. As long as it exists, I think it's immortal, so it's okay. I appreciate everything. This was lovely. Thanks, Jinlan, and you
Thank
do a
Yeah,
you.
great
Jinlan,
job.
that was fantastic.
And like you
Lots of good
say,
information.
you've got many things coming up this year, more than normal probably. You're probably every month putting together some webinars on your own, and we will probably probably crack in and put some things out there again on something specific that maybe isn't automotive, but is just as interesting. So good job by you. Thank you.
Thank you very much.
Yeah. And let's see. I think that's mostly everything, unless there was anything we missed. And if, like you say, Dave, if you've got a question we didn't get to, or you just think of it later when you're watching this again, just send us a note and we'll pass it on and answer it. That's what we're here for. Once again, coming up, we have the APDA will be next week in Barcelona at the ISE. So check us out. Try to find the booth where the OCA is, and that is in Hall 7. That's E260 is the booth number. 2 p.m. Wednesday.
Yeah.
A little meetup there.
Right.
So come by and say hello and look for that guy walking around if you can't find him at the booth. So. And we'll have some more coming up again. As I mentioned, we're working on talking about something that's probably relevant to everybody at this point, or at least considering the scenarios of tariffs and how we do our business in the future for product development. That's planned for the latter part of February is what we'll have it out. And we'll make sure everybody knows about it. But you can subscribe to our YouTube channel, find out more, keep in touch with us. We're growing and we're going to keep getting bigger. The next year is going to be full for us and for you who follow us. So please do. And yeah, follow us on LinkedIn as well. So I think that's everything we've got. This will be on the channel once we finish. You'll be able to find it and you can share the link and follow us again. So thanks again to everybody. And is there anything else we've missed? Anybody? I think we've covered it. So I appreciate the time.
I think we're good. Like,
And
subscribe, share, all that good stuff.
all the good things. Yes. Thank you, everyone. Thank you for your time.
Thank you.
Jinlan. I appreciate that as always. And that should do it for us. I appreciate it. So thanks everyone for watching.
Yeah. Have
Yeah.
a good day.
Have a great day.
Thank you.
Bye-bye.